Today we're going to go over a dimensional analysis, and specifically for this problem we're actually going to use the Buckingham Pi Theorem. And so the Buckingham Pi Theorem basically states that we need to find n variables that are made up of n dimensions, and those will determine the k number of pi groups that we need. So basically it's represented by this expression here, which is n minus m is equal to k pi groups. And then so in order to determine this, we are going to use, whoops, I don't know what happened there. In order to determine this, we're going to go through this problem here, which is basically, it says the heat transfer rate per unit area Q to a body from a fluid in a natural gravitational convection is a function of the temperature difference delta T, gravity G, body length L, and three fluid properties, kinematic viscosity, conductivity, and thermal expansion coefficient. We're going to rewrite it in dimensionless form with the understanding that it is known that G and beta appear only as the product G times beta. So in our problem here, we see that Q, which is a function of delta T, G, L, kinetic viscosity, K, and beta. So we see if we count out these variables, we have Q. So 1, 2, 3, 4, 5, 6, 7, seven total variables. Now, in each of these variables, they're made up of dimensions, units of measurement, which we define as dimensions. So, for example, G is going to be equal to meters per second squared. So it's made up of the two dimensions, meters, and then seconds squared, which is time. So in order to represent this in dimension quantities, meters, which is a dimension of length, will be represented as L, and seconds, which is a dimension of time, will be represented as T, and then it's second squared, so it's T to the minus 2, which it's also fine, obviously, to write it this way. I just have the preference of writing it that way. And so we need to do this for all the variables. So for example, Q, which if you don't know what these are, more than likely your book will provide what makes up these, what dimensions make up these quantities. So you might have like a table or something to refer to. But anyways, so we have Q, which is heat transfer rate. That's just represented as m T to the minus 3. We have delta T, which temperature dimensions quantity is capital theta, which is just kind of, that's how I do my capital thetas. It's like a little H with a circle around it. But anyways, length is easy. It's just L. Kinematic viscosity is going to be L squared T to the minus 1. And then, K is going to be, let's see here, ML capital theta to the minus 1, T to the minus 3. And then beta, heat expansion, thermal expansion coefficient is just 1 over temperature, which I'll just represent like so. And so now we need to go through and see what dimensions make up all of these variables. So quickly we see that length, time, temperature, and mass are all dimensions that make up these variables. And other than that, those are the only unique ones. Afterwards, they just repeat themselves. So that tells us that we have four fundamental dimensions that make up these variables. So then we can use Buckingham Pi Theorem, which is just n minus m, 7 minus 4 is equal to 3k pi groups. So we have 3 pi groups that we need to determine from this to represent the dimensionless groups for this problem. And so in order to do this is a little bit of an arbitrary process, but we're going to need to pick 4 variables since we have 4 fundamental dimensions, and those variables together need to make up all of the, each of these 4 fundamental dimensions. So I'm going to pick ones that are kind of the most simple versions. So for example, delta T is just, the temperature dimension by itself. L, which is just the length dimension by itself. I'm also going to pick G because that has time in it, so length, per unit of time squared. And then I still need to get, mass, and so I can choose Q or I can choose K. In this case, I'm going to choose K just because Q is dependent on, these remaining variables, and so that's just purely, my own, choice. From there, though, now that we've chosen 4, what are considered 4 repeating variables, the remaining 3 are going to be used. Each one is going to be used to make up each pi group that we have. So 3 pi groups, 3 remaining variables, 1 for each pi group. So I'm going to start, I'm actually going to start with kinematic viscosity here as the first, of the three remaining variables to make up my first pi group. So in order to do that, to start this systematic approach for, creating dimensionless quantities, Buckingham Pi Theorem basically says we have pi group 1, which is made up of delta T, G, L, K, and then finally kinematic viscosity, so the process goes like this, where we basically represent our pi group as m, which is mass to the power of 0, L to the power of 0, T to the power of 0, and then temperature to the power of 0 is equal to these variables here that we want to represent in their dimensions. And so I'm actually going to move this down here so I have some room. So basically delta T, we already determined, is sigma H. And so each of these variables, we're going to raise, each of the repeating variables, we're going to raise to some arbitrary exponent. So in my case, I just decided to choose A. You can choose whatever you want. I just chose A. G, which we determined as M to the, L T to the minus 2 raised to the power of B, again, arbitrary choice. L, which is just length, raised to the power of C. K, which is just going to be M, L, capital theta, raised to the power of D. And then let me write that better. And then kinematic viscosity, which is just L squared T minus 1 raised to the power. And now in this case, after our repeating variables, we're going to raise those to an arbitrary exponent. The remaining variable that is to make up each of the pi groups will be raised to the power of 1. So just an important thing to note there is that the repeating variables will be raised to arbitrary exponents, whatever you choose. I chose A, B, C, and D. And then the one remaining variable that's going to be crucial to each pi group will be raised to the power of 1. So now I need to isolate each dimension and show it as, or represent and see which variables make up that dimension to help me determine what these, like what A, B, C, and D, what these exponents should be. So I'm going to start with M, and what this says here is that there's 0 of the mass dimension on the left-hand side, and then I'm going to go through each variable to determine which one has mass. So this one doesn't have mass. Gravity doesn't have mass involved in it. Length doesn't have mass involved in it. We see here that K does have mass involved with it, and kinematic viscosity does not. So what that basically says is that we have M essentially to the power of 1 times D. So we have 0 equal to D, which just says that D is equal to 0. And I'm going to do this for each dimension. So next I have L, which again is just 0 on the left-hand side. Go through my variables. I see this one doesn't have it. I see this one has it. I see length obviously has a dimension of length within it. Again, K has it, and also kinematic viscosity. So in order to represent this, I need to put L, which is just, since we have one L, it's just B, one L for C, which is just plus C, one L for K, which is just going to be plus D, and then I actually have two L for kinematic viscosity, and so since it's raised to the power of 1, that's just plus 2. And so now I know that D goes to 0, but I can't figure out what B and C are, so I'm just going to move on to the next dimension and do the same thing again. So I have 0, which is equal to, well, B is raised to the minus 2, so it's minus 2B. And then L is 0, there's no one there. There is one in K, which is to the minus 3, which is minus 3D. And there is one in kinematic viscosity, which is just going to be minus 1. So again, D goes to 0. I can solve for B and see that B, add the 1 divided by negative 2, B is equal to negative 1/2. We can do the same thing for temperature. Oops. 0. So I see that A has a dimension of temperature in it, and I see K has a dimension of temperature in it, and it's minus 1, so that's just minus D. Again, D goes to 0, which just means that A is equal to 0. And now I can actually go back to this step and solve for C, and plug in B. So B is negative 1/2 plus 2 is 3/2, minus it over. That means C is equal to negative 3/2. And so now, essentially, I have my first pi group, which can be written like so. So pi 1 is going to be equal to, well, I still have the kinematic viscosity, which is this term here, raised to the power of 1. So I have kinematic viscosity all over, well, we have B, which is gravity, is raised to the negative 1/2. So that goes on the bottom, and I'm just going to represent it by the square root sign. And then I have C is raised to the negative 3/2, which is L, so that goes down here. So we have the cube root of L. A is 0, so temperature is just to the power of 1, where delta T is just the power of 1. It's not going to show up in the problem. D is also the same thing, K is to the power of 0, which is just 1, so it doesn't show up as the problem. I'm actually going to represent this. I'm going to square this whole equation and get V squared over G L cubed. And so this right here is our first pi group. And we're going to repeat this exact same process for the remaining 2 variables. So in this case, we just did kinematic viscosity. Out of the 4 that we had, we need to do Q, and then we also need to do beta. So next I'll do Q. So for Q, again, same thing. So pi group, and now this one's 2, is going to be delta T, G, L, K, because those are the same remaining variables that we had from the original, what we originally determined. And then finally, we have Q, which is one of the remaining variables, and then we're going to represent it the same way, go through that same systematic approach. M to the L, M to the 0, L to the 0, T to the 0, capital theta to the 0. Same thing, just going to repeat the same process. So L, T, represent everything in its dimensions, fundamental, like the base dimensions. So there's that. See, again, every repeating variable gets raised to an exponent. Every repeating variable gets raised to an arbitrary exponent, and then so forth. And then finally, we have Q, which is going to be raised to the power of 1, but we see here Q is mt minus 3 raised to the power of 1. Okay, so same thing again. Isolate each dimension. 0 is equal, well, the only thing that has mass in it is D, which, D, and then also actually Q does, so we have D plus 1, which means that D is equal to negative 1. Same thing for length, 0, because again, it's 0 on this side. We have 0 dimensions of the length. So again, we'll go through the same thing. We see here there's 1 length dimension in B, so that's B, 1 length dimension in length, which is C, 1 length dimension in K, which is plus D, and then we have none in Q. Once again, though, we can't solve for B or C because we don't have enough. We have too many unknowns. Next, we'll go on to T. So 0 is equal to, well, B has 2 time units of the time dimension within it, so it's negative 2. B, same thing for D, is minus 3. D, and then Q again. Q actually has 3 units, or like 3 measurements of time within it, so it's negative 3, because negative 3 times 1 is just negative 3. And we can solve for B, so we know that D is equal to negative 1. So negative 1 times negative 3 is just positive 3. Positive 3 minus 3 is 0, which means 0 divided by negative 2 makes B equal to 0. Finally, we can do this for temperature. Same thing, 0. We have A minus D. We determine that D is negative 1, so negative times negative 1 is 1. So A plus 1, add 1 over, we get A is equal to minus 1. And then we can, again, solve for C now. So B goes to 0, D is negative 1. So C minus 1, add the 1 over, is equal to C is equal to 1. So now we can make up our second pi group, which pi 2 is basically equal, well, we have our cubed raised to the power of 1, so we'll leave that up here. Let's see here. So C is equal to 1. So that means that essentially what we